Hi, hello. Welcome to our YouTube channel. So, by the way, if you have not subscribed yet to our channel, please click subscribe. We will be downloading videos every day. Okay, so we will be discussing in this video regarding steel connection. Steel connection. Okay, so here in this video we will discuss. This is similar to a board exam question, multiple choice. So we will find the allowable load on the connection based on gross area, based on net area, and based on block shear. Most students, most reviewers students had a hard time understanding the block shear. Okay, so this is the question. The butt connection. So this is a butt connection. The main plate are joined, and then side plates are provided. So we call them splice plates. Okay, so the butt connection consists of 822 mm diameter, 8325 bolts, spaced as follows. So we are given the distances, spacings S1, S2, S3, S4, yes, up to S4. And then the plate thickness, T1 is 16 mm, the main plate, and the side plates are 12 mm. Well, if you can notice, the side plates 12 mm, the main plate is 16. So if you combine the total thickness of the side plates, that will be 12 plus 12, that's 24. So obviously the side plates will not govern the block shear and the gross area. So that's automatic. So we will be focusing on the main plate here, the 16 mm thick. So we are also given the yield strength of the material, Fy, Fu, ultimate strength, allowable stress on gross area. So this question is ASD. So this is based on ASD. 148 MPa, allowable stress on gross area, on net area, allowable shear stress on net area, allowable bolt shear 120 MPa, and the bolt hole is 25 mm. So we are to compute the value of P based on the following criteria: based on bolt, based on gross area, based on net area of plate, and based on block shear. All right. So this is now the dimensions reflected here. Okay. So let's start with the first part. This is the easiest. Based on gross area. The allowable stress on gross area is 148. Actually, that is 0.6 Fy. But she gave the value already. So we can use that directly. So in part 1, so we compute the gross, the tensile stress. The tensile stress is the force, P, divided by the gross area. Right? And that must not exceed the allowable stress of 148 MPa. That's how you should solve this kind of problem. When if ever there is a given allowable value, do not use equal sign. You use inequality. When you say shall not allowable, meaning the stress must not exceed. So it has to be inequality. Okay. So with that, P is the one unknown. The gross area is, okay, let's get the gross width. The gross width of the plate is 80 plus 240 mm, so that's 160 mm, and the plate thickness is 16 mm. So we will go directly to the main plate. For the side plates, it will be 12 times 2, that's 24. So obviously it will not govern. So it will be the main plate. So P is unknown, the gross area is 160 by 16, and it must not exceed 148 MPa. So with that, then P must not exceed 378.8. So what does this mean? So P can have any value as long as it will not exceed 378.8. So technically, there are two choices of this in this that are qualified. 254 and 378. But among the two, this is the greatest. Of course, that will always be the case. Because sometimes the examiner is asking, select the maximum. Students try to round this off. So the maximum meaning the maximum that is qualified based on your criteria. Because we call this criteria. Criteria. So yun. P shall not exceed 378.8. Okay. The next is based on net area. Based on net area. So the same equation. So the tensile stress is equal to P divided by the effective net area. So we need to compute the effective net area, and it must not exceed the allowable tensile stress on net area, which is 200 MPa. All right? Okay. In this problem, the effective net area is the actual net area. The actual net area. So there is no zigzag pattern here. The bolts are arranged along the same line. So the effective area is equal to the actual net area. So what is the actual net area? What part will tear off here? So if you consider this side, now due to P, this part is the critical. This part here. Okay, if you cut that cross section, if you cut a cross section here or a section at that, it will look like this. That the height is 160 mm, is one, and there will be two holes. 16 mm, the thickness is 16 mm, and there will be two holes. The holes are 25 mm. Okay, so actually, the code says the hole diameter must be taken as 1 point, based on the 2001 code, it shall be taken as 1.6 mm larger than the hole diameter. So we should not use 25 supposedly. But in her choices, there will be no answer if you will add 1.6 mm here. So let's just use that hole diameter. So computing the net area, that will be 160 mm less two holes, 25 times 2, times the thickness of the plate. So this is your net area. So there is no reduction factor because this is a flat plate. Unlike if it is angle and then connected on one side only, then you need a reduction factor U. In this case, it is equal to the actual net area. But you have to verify the 85% because we have here splice plates. You have to check on the 85% limit for splice plates and gusset plates. It is written in the code. The 85% for the splice plates are 12 mm thick, 160 mm wide. If you check on that, 160 mm times 12 times 2, because there are two plates, 85% of that is 3,264. And obviously, this is even less than that. So 1,760 is okay. Because, for example, if this turned out to be 1,500 mm squared, then you have to use this one. Okay, so you do not only consider the main plate, we have to consider the splice plates, and this is the limiting value. Even in the new code 2010 and 2015, there is this provision also for splice plates and gusset plates. 85% of the gross area. Okay, so we already have the effective area, then substitute it here. So P over the effective area must not exceed the allowable stress of 200 MPa. Then we get the P. So P must not exceed 352. So any P value not exceeding that is qualified. So the practical choice here is letter A. That's the advantage of using inequality because you don't have a hard time on choosing whether you choose the higher value or the smaller value. If you're using inequality, then it's very easy to choose what is the proper. So that's always the case if there is involved or allowable stress involved. It has to be inequality. All right. Then the third part, okay, is the part where most students had a hard time understanding this one, solving this problem. In our review center, we have, other than the scores, we have statistical, we have complete statistics. So the result of the scores are, we can get which problem had the smallest statistics when it comes to the correct answer. And this is one, the block shear. Okay. For the block shear, okay, this is it. Now, block shear is combined tension and shear. Combined tension and shear. So let's consider the main plate. Let's consider the main plate. All right. So if this force is applied, then this row of bolts here, possible mode of failure is shear will occur along this blue line here, shear, and tension here, that red. Okay. So, and it will fail like that. Ayan. Is that clear? So that's one possible path, block shear or shear rupture. Okay, so all you need to compute are the areas in shear and in tension. Okay, the tension area will be 80. Look at the thread. The thread is the tension. It will be 80 mm less 2 1/2 of the whole. So 2 times 1/2 of 25, or that will become 25. Okay, times the thickness of this plate, 16 mm. So that is the tension area. The shear area will be 150 mm minus 1 1/2 of the whole diameter. Okay, 150 minus 1.5 of 25. The whole diameter is 1.5 because there is one and another one up here. Okay, times 16 mm, the thickness of the plate. And take note, there are two shear paths here, this one and that one. So you multiply that by 2. You multiply that by 2. So this is your shear area, 3,600 square mm. Okay? So finally, the value of P equals the allowable tensile stress, which is 148. Net area, 200 on net area times the tension area plus the allowable shearing stress, which is 120 times the shear area of 3,600. Okay, did you get this? This is the allowable tensile stress on net area, not this one. This is the gross area. This is the net area for tension, and this is the allowable stress for the shear. Okay? So that will give you P equals 608 kilonewton. 608. Actually, that should be inequality. It must not exceed 608. But that is based on this possibility of failure. Another path that you have to consider is, okay, shear along this line and tension along this line. All right? Going through the bottom. So, hindi na siya gaganon dito. Diretso na sa ibaba. So that this will be sheared off. Get this. Okay? That one. So, the same as what you did here. Let's identify the tension area. The tension area will be 120 less 1 1/2 of the whole. This one. Times 16. All right? 1,320. No more times 2. Only 1. And for the shear, it will be the same with this. Wala lang yung times 2 natin. The same with that, but there's only 1. There's no more shear on this end here. So that will be 1,800. Okay? So substituting to this formula, we have allowable tensile stress 200 times the net tension area plus allowable shear stress times the net shear area. And that gives you 480 kilonewton. So there are two possible values, but of course we are looking for the critical, the most critical, of course the lower of the two. It should be 408. Okay? 480. So the answer here is letter A. Okay? So I hope you learned something from this video. We will have more samples. Give us time. We will do it every day. We cannot, there's lots of requests now that we receive about the topic. We will do it. We have just launched our YouTube channel in less than a week. But we'll be doing it at least 2 videos per day. Eventually, we will have collection of different videos in all different subjects. Okay, so thank you so much, and don't forget to click subscribe button here and click on the bell icon so that you will receive regular updates on the latest video uploads we have in our channel. Okay, so thank you so much.